Welcome to the video on Year 13 Applied Chapter 4 Moments, Section 5 Tilting. What we're going to look at here is the case where you've got a rod on two pivots, and what happens just before the rod starts to rotate. Okay, so if you imagine we've got Lewis here on the left, we've got this rod. It's rested on both A and both B. Before Lewis gets there, the rod's nicely set on both A and both B. Where Lewis is, I could, instead of putting Lewis on there, I could add weights, keep adding weights on that section. Nothing's going to happen at first if I add a small weight, and eventually, if I put a massive load on there, this weight's going to be so big that the moments here going anti-clockwise is going to be bigger than the clockwise moments. So the rod is going to rotate in an anti-clockwise direction about A. Just before, at the moment before the rod rotates, if I put just enough, the rod hasn't quite rotated, what you'll find is that all the force is going, the reaction force is at A. At B, it's just about to leave, just like you've got your gap there in the diagram. It hasn't quite left B, it's just on the point of rotating, so that all the force is focused on A. So at the point the rod is about to start tilting, okay, then all the reaction forces at A, there's no reaction force going on at B. If you put the slightest bit of extra weight where Lewis is there, then the whole rod's going to start rotating. It's just touching here, and it's just about to lift off and start rotating. There isn't any force going on at B. Okay, can you have a little go, bearing that in mind, can you have a little try at this question here for me, please? If you put me on pause and then press play, and I'll start talking in a second. Okay, again, key thing, draw your diagram, put everything in. Because it's saying it's on the point of tilting, what it's telling you is it's about to start rotating anti-clockwise, so it's about to start pivoting around C. Okay, the weight's so high here that this is about to start going down here, so this is about to start lifting off. It hasn't lifted off, it's just rested, it's just touching at D, but there's no force there at D at all. So this point of tilting is telling me there is no reaction force at D. Okay, I don't know what the reaction force is. I also don't know what Lewis's mass is. So if I take moments about C, because my line of action of force goes through C, I won't need to worry about the forces at C. So by taking moments about C, I've got my weight of Lewis and my distance of 5 going that way. As my anti-clockwise, and my clockwise ones are my 3 meters multiplied by my mass of the beam times G. And the only thing I don't know there is the weight of Lewis, so I can work out what Lewis's weight and Lewis's mass is, which is 27 kilograms. Okay, another one for you to have a go at. Again, diagram's key. Put me on pause, have a try at this, and then press play in a second. Right, let's have a look at the diagram. So non-uniform, so your centre of mass doesn't have to be in the middle. So this time, rather than you being on two pivots, you've got it suspended by 2 wires, you've got 2 tensions. It's on the point of rotating. So you've put this weight here, so all of a sudden this is really heavy. So it's on the point of this thing rotating in an anti-clockwise direction. So what's going to happen is this it's going to rotate about point C, and this thing's about to lift up. So even though you've got a cable D, where D is here, because you're about to rotate, this is about to lift off, it's just attached to the cable. The cable hasn't got any tension at all because it's about to start moving up in that direction due to the weight there. So again, it sort of makes sense to take moments about C. If you take moments about C, you don't need to worry about the tension at all because the line of action of the force is going through C. You've got your force times perpendicular distance for your anti-clockwise. The distance, centre of mass of the rod from A, so we've defined that as X. So you know that bit's 3. You're taking moments about C. So your remaining distance here is your full length X less than 3 meters that is there. You've got a distance of X minus 3. You've got a weight of 40 newtons. So the only thing you don't know is the X, which you can solve to find. Okay, try this exam question, please. And if you pause me. Okay, key thing, draw your diagram. Don't forget to draw your diagram. Centre of mass of the beam, right. Total length of the beam is 15 meters. So at A, I've got 50G going down. I would have put that on my diagram as well. Okay, so when I stood at A, you're in the point of tilting. Okay, so if I take moments about P, when the child stood at A, I've got 50G times 2. I've got the centre of mass of the beam, if I define that as X, times X minus 2. When the child is stood at B, if I take moments about Q, I've got 50G times 3. And I've got a distance from X as my centre of mass. The whole thing, if I'm going from there, the whole distance is 15. I'm going from 3 meters. So, so that remaining distance is 12. So the distance from here to here is a full distance of 12 less the X that it is there. So it's 12 minus X. What this question is getting at, basically, when the child was stood at A and you were taking moments about P, because it's on the point of tilting, there's no reaction force at Q. When the child was stood at B, it was on the point of tilting about Q, so it's going to start rotating that way, so there's no reaction force at P. Once you've got those two equations, it's just a matter of solving the two simultaneous equations. You've got two unknowns, M and X. So with two simultaneous equations, you can rearrange to get either M on its own or X on its own and substitute into the other equation and solve the algebra. So M is equal to 25 kilograms and X is equal to 6. Part B. Okay, so now you need the particular place where the child's going to stand so that the reaction force at P and the reaction force at Q are the same. Okay, we've seen when the child stood at A, there was no reaction force at Q. When the child stood at B, there was no reaction force at P. But there's going to be some point where the child could stand where your two reaction forces are the same. Okay, so if we take The normal tools are we can resolve vertically, we can resolve horizontally, or we can take moments about a point. So if we resolve vertically, I've got R going up at P, R going up at Q. I've got the mass of the beam, which we know is 25 kilograms from part A. So I've got 25G as the force from the beam and 50G as the force from the child. So I've got just one unknown there, so I can work out what R is. If I take moments, there's lots of different places you could take moments. Here they've just taken moments about A, one end of the beam. So I've got 2R is going anti-clockwise. I've got the distance to the centre of mass of the beam, which is 6 meters, which I've worked out from okay, sorry, it's got the 12R there. I'll just do that one first. So the 12R is you've got the other reaction force. The beam's 15 meters long, you're 3 meters in. So that's 12 meters times R. So that's your other force going in a anti-clockwise direction. So your 2R and your 12R going anti-clockwise. Going clockwise is your 25G times your distance of 6 meters that you found in part 2, plus your child's weight, which is 50G, times the distance from A to where the child's standing, which is the AX that you don't know. So the only thing that you don't know is the distance AX. So therefore, you can solve this equation and find out what the distance AX is, which is 7.5 meters. Okay, can you have a go at some of those questions, please? Got to do 1 to 6. Bonus question 7. Don't forget, there's loads of good questions in the mixed exercise, I should say. Exercise 4, page 85. Thank you for listening.